Now that we've introduced some terminology and notation, let's talk about matrix arithmetic. This presentation has a table of contents that we'll revisit as we go through the sections, mainly because there are a lot of details here and it's easy to get lost in what we're talking about. But we'll start out talking about the element-wise operations, or matrix addition, subtraction, and scalar multiplication. Two matrices or vectors can be added or subtracted if and only if they have the same size. This is because when we perform addition and subtraction, we add and subtract corresponding elements. Throughout this presentation, I'll use visual representations like you see here. For example, this matrix A, each green box represents one number or an element in the matrix. Algebraically, the formula for addition or subtraction looks like this. And this says that the ijth element of A plus B is equal to the ijth element of A plus the ijth element of B. So visually, if I want, in this example, the 3, 2 element of A plus B, I just add the 3, 2 element of A and the 3, 2 element of B. So addition acts element-wise. Some quick examples just to make sure we understand. Part A, compute A plus B if possible. And this addition is possible because A and B are both 3 by 3 matrices. So we just add corresponding elements. 2 plus 4 is 6, 3 plus 5 is 8, and so forth. Part B, compute A minus H if possible. And this would not be possible because we don't have an element in A for every element in H. These two matrices do not have the same size. Another operation that acts element-wise is scalar multiplication. This is where we take a constant, just one number, and multiply it by a matrix or a vector. The result is the scalar multiplied by every element in the matrix. Again, algebraically, we'd write that the ijth element of alpha m is equal to alpha times the ijth element of m. Let's take a geometric look at what happens when we add vectors or perform scalar multiplication. First, I want to reiterate this idea that points and vectors are pretty much interchangeable ideas. Here I have this point A plotted on a coordinate plane. Its x-coordinate is 1, its y-coordinate is 2. And I can also think about A as a vector. And a vector has both a direction and a magnitude. The direction of the arrow points away from the origin to that coordinate point. The magnitude is the length of that arrow. We'll talk a lot more about magnitude later in this course. For now, you can think about Pythagorean theorem and looking at A as the hypotenuse of a triangle, where one leg of the triangle has length 1 and the second leg of the triangle has length 2. And so the magnitude of A, measured in this way, would be the square root of 5, the square root of 1 squared plus 2 squared. Again, let's look at that vector A, which is a point, and let's think about what happens when we multiply A by a scalar. If I multiply here A by 2, the vector points in the same exact direction as A, and its length is doubled. Now, if I were to multiply A by a negative number, the direction of A flips through the origin and points in the exact opposite direction of A. And in this case, since the scalar is less than 1, the result is shorter than the original point. And this is precisely the reason why we call single numbers scalars, because they scale vectors in space. When we perform vector addition, the idea is that you have an object at the origin and you move it in the direction and magnitude of A and then in the direction and magnitude of B. This is like taking one of the vectors, here B, and placing its tail at the head of the vector A. The result is where you would end up, or where that object would end up after it was moved in the direction and magnitude of both A and B. Now, of course, it would be the same if I took the vector A and placed its tail at the head of the arrow of B. Addition is still commutative in linear algebra. Let's take a look at one application of these ideas with data. Now, suppose I have these 5 purple data points, which again can be thought of as vectors, and I also have their mean. Now, this is called a centroid in linear algebra, and it's just the point that has the average here of the x1 value and the average of the x2 value. And what I want to do with this data is I want to subtract the mean from both x1 and x2. I can do that all in one operation using the vectors that are here. These purple vectors represent my data points, and the green vector represents the centroid. So I want to subtract the green vector from each of the purple vectors. To subtract, what I'm really doing is I'm adding the negative. And again, the negative of that green arrow is the arrow with the same length that points in the opposite direction. So taking the negative of the green arrow and placing it tail to head of the purple arrows results in this picture. And the result is where I'd end up. So these purple points, once they are centered, or once the mean is subtracted, end up at their final location. And now the green arrow would end up at the origin because the new mean of the data is 0. Centering the data really just involves a translation of the data so that the center of the data cloud is the origin. Now let's combine the ideas of scalar multiplication and addition and talk about linear combinations. Linear combinations are really the foundation of a lot of things we'll do in linear algebra. A linear combination is just a weighted sum. You have some scalar coefficients here written as the alpha i's, and you have some vectors, bi, and you're taking a weighted sum of those vectors. There are many instances where you'll want to do something similar to this or interpret something that looks like this. The simplest linear combination might involve columns of the identity matrix. You might recall we call these elementary vectors. Here, I've taken a 3-dimensional vector and broken it into a linear combination of elementary vectors. You can see this is not complicated. The coefficients become the elements because of the way these elementary vectors look. You can picture this as a breakdown into parts, where each of these parts give directions along the 3 coordinate axes. And we'll get to this idea, this precise example, in just a minute. But first, let's lay some groundwork. When we look at linear combinations geometrically, we're just combining the idea of scalar multiplication and addition. So if I have A and B, I can form the linear combination a minus 3b by taking the vector that's 3 times the length of b in the opposite direction of b and adding it to the tail of a. The result would be a minus 3b. Now, revisiting this simple linear combination we talked about and picturing a three-dimensional space, what this equation tells us is that we should go 3 points along, a magnitude of 3 along the first axis, a magnitude of negative 2 along the second axis, and 4 along the third axis to end up at our point, which is 3 minus 2, 4. So in a way, these coefficients represent this breakdown into parts of this overall point. This may seem a little abstract right now, but it's something that we're going to capitalize on when we talk about principal components analysis. A linear combination does not always have to involve a weighted sum of vectors. Really, it can be a weighted sum of any type of object, like a matrix. In a very similar example to what we just looked at, I can write this matrix, this 2 by 2 matrix, as a linear combination of these, say, elementary matrices. And the solution should be rather simple to see. The coefficients will just be the corresponding elements in the matrix A. Now that we've talked about the element-wise operations of addition and scalar multiplication, let's start talking about multiplication. And we'll start with the inner product and matrix vector multiplication. First, we're going to make a little note about notation. Throughout this course, and in most resources that you'll find online, unless it's otherwise specified, all vectors should be assumed to be columns. This simplifies the notation because if x is a column vector, then you can automatically assume that x transpose is a row vector. And therefore, the dimensions of a vector are automatically specified in the context of the problem. The vector inner product is the multiplication of a row vector times a column vector. This is known in the broader sciences as the dot product. So if you've taken Calculus 3, you may have been introduced to this as the dot product, or in physics. And the result of this product is a scalar. So I multiply a row times a column and get a scalar. Visually, here I have A transpose, which is a row, and B, which is a column, and again, the result is a scalar. The algebraic formula here is A transpose B is equal to the sum of the corresponding elements of A and B multiplied together. The way I like to see this in my brain, we take that purple vector and it flips over on top of the green vector, multiplies each corresponding element, and adds across. Obviously, A and B, the green and the purple vector, must have the same number of elements in order for this to line up and work. Let's look at some concrete examples. If possible, we'll compute the following inner products. X transpose Y. X transpose, 4 elements, Y has 4 elements, so we can indeed perform that multiplication. Here, written out, we have X transpose times Y. Again, multiplying corresponding elements. -1 times 3, plus 2 times 5, plus 4 times 1, plus 0 times 7, adding up the result to get a scalar single number, 11. Next, we'll try X transpose V. Now, X transpose, or X, only have 4 elements. V has 5 elements, and so this multiplication will not be possible. Finally, V transpose U. Both of these vectors have 5 elements, so the multiplication is possible, and when we multiply corresponding elements and add across, we get 6. Here's a place where you can check your understanding and do a couple of examples to make sure that this is clicking. Pause the recording, and when you come back, you'll see the solution. Here's the solution. Next, we're going to talk about matrix times vector multiplication. And we're going to look at the inner product view of this. Now, in this presentation, we're going to look at matrix vector multiplication and matrix multiplication through a few different lenses. But no matter what lens we're looking through, the product is the same. The operations that are going on are always consistent and will always yield the same exact product. There's just some ways that we can manipulate the way that we look at this to be convenient in different scenarios. So here I have a matrix, the green, times a vector, the purple, and the result of this will be another vector. Now the inner product view in my brain, that purple vector picks up, turns on its side, and it moves down the rows of the green matrix, forming an inner product at every row. The sizes here must match up. So if the number of columns in the green matrix is 3, it must be that the number of elements in the purple vector is also 3. So like I said, that purple vector moves down, multiplies every green element, and then adds across, making an inner product at each row, and the red number is the scalar result of that inner product. And the result of the multiplication is this vector that contains the inner product of every row in the green matrix with the purple vector. Sorry, so in finality, the green matrix is 5 by 3. The purple vector is 3 by 1. And the final result is 5 by 1. Now, pretty soon we'll talk about how those dimensions have to line up in a more specific written down context. Just starting with an example, we want to determine whether the following matrix vector products are possible. And if they're possible, we'll compute the product. The first one is A times Q. Now again, if we visualize this as the green matrix and Q as the purple vector, when I pick up Q and turn it on its side here, you can see the dimensions will not line up because Q has 3 elements and A only has 2 columns. Now this is one way to look at writing that down. When I say the inner dimensions do not match, A is 3 by 2, Q is 3 by 1, and so when I say these inner dimensions, I mean the numbers on the inside of these 2 parenthetical dimensions. We'll talk more about this in a minute. A times V, those sizes look like they will line up just fine. And so I take the inner product of every row of A with V, and I get a result. Let's look at that same multiplication, a matrix times a vector, but from the view of a linear combination. Again, I have my green matrix times my purple vector. And what we just saw, the inner product view, is completely equivalent to what you're about to see. Again, multiplication is only defined in one way. It's about the way that we might view it in our brains, or the way that we might write it with our pencils, that can sometimes reveal interesting patterns about what's really going on. So this is how I view the linear combination view. Matrix vector multiplication is actually a linear combination of the columns of the green matrix, with the coefficients coming from the purple vector. This is really an important idea. If we look at our previous example, where we multiplied A times V, this was the inner product view, where we wrote the inner product for every element. Another way to look at this is to take that 3 and put it in front of the first column, and the 2 and put it in front of the second column, and you can see that nothing changes in this calculation. 3 times 2 plus 2 times 3. This is 3 times 2 plus 2 times 3. That completes this recording, and when we come back, we'll be talking in detail about matrix multiplication, again from a few different viewpoints, and then we'll revisit vector multiplication in a different way, looking at the outer product.